Welcome back to day 109. We're back once again. I just wanted to start that video with a bit of a soul-staring session. So I hope you're feeling intimate. Because that was an interesting experience. And I feel like I know you better. Okay, let me stop being weird, but we're back once again. Yeah, I forgot what we were talking about yesterday. And I always forget what we're talking about between videos. It all kind of feels like a blur. So at the end of the day, sometimes I can't even tell if I've already done LeetCode or not. And shout out to my homeboy Gabriel, who let me know that I uploaded the wrong video yesterday. So I accidentally uploaded 107 by mistake, and then we were able to re-upload 108. So that was pretty awesome. Thank you once again. Also, we have some comments. Come on, man. Now all the fans wondering what this application is. Can't wait for the reveal. Hopefully after you read this comment. Also, this format where you read the comments for the video, I think is genius. I might see this for my video, so thanks. So I actually stole this from someone else. I saw this at another YouTuber was doing it. Actually, a friend of mine, and I was like, oh, I gotta do this. This is pretty cool. So, now I'm going to watch and comment on your most recent video. I hope I make the cut. I will comment on your next video. Hopefully I make the cut. And hi dude, today I released my first LeetCode badge. Let's go. Let's go. I don't know what a LeetCode badge is, but legend. Actual legend. I wish I had a LeetCode badge. But I actually don't know how to pronounce this name. So actually, if someone does, that'd be pretty cool to know. But they look like some interesting hieroglyphs. I think it might be Russian, but I'm not certain. So, very cool name though, it seems. But we are back once again, and we were stuck on a problem yesterday. Actually, what I was gonna say is I think I've been rethinking the structure of the grind. I think I'm definitely going to slide it back a little bit. It's very interesting because I think we're now entering a pattern where I'll do an hour of LeetCode for like 2 weeks straight or 1.5 weeks, and then we'll go back down to 30 minutes. And it's just interesting. I think maybe it's actually hard to keep the LeetCode at an hour because I'm noticing the videos end up being an hour and 15. So maybe that's because I'm reaching my max cap that the Huberman Lab podcast, the Buffett scientist on the internet, mentioned at 1 hour and 30 minutes is the ideal study time. But I'm not certain. And I also think it's just other stuff outside of LeetCode. But first and foremost, it must stay sustainable. And yeah, I have quite a few application ideas in mind. I'm not exactly certain. Not exactly certain that they're all bangers, but we're gonna try and make them. And I think, I don't know if they'll be profitable. So we shall see. And yeah, I always think it's cool. I think there's another YouTuber, Ben Awad, who has like a startup style like content pipeline. I think that's pretty cool. Maybe we could do something like that in the future. That'd be really, really hype. But that being said, who knows? So I think I actually don't have a lot to say today. Maybe that's a good thing. Maybe that's a bad thing. But I think we're just going to jump into it with an hour. I said I'd read the ADM again before NIM game. Maybe this is also a problem with the whole system. I didn't even get a chance to read the ADM. So, yeah, I don't really know. I think I need to take a closer look at the schedule to see why I'm missing so many I'm not even missing that many objectives, but maybe the bar is just too high. And I'm trying to hit too many things. Maybe I should just try to hit the highest priority things. So, I think I need to look into that. But I think there's also another issue that I don't know what do they call it? They call it the flow state or something like that, where the level of difficulty that your environment requires from you and your level of skill level are like really, really close. And then that's the flow state where it's just within your ability, but just outside, so that maybe the process of bridging that gap centers your mind and you kind of enter the flow state. There's also another version of that when they talk about learning, and the optimal learning is something where it's like it's in your space. If it's something you already know, you kind of tune out. Because I think someone wrote a really good article on like the brain's natural like entropic properties or something like that. Or like if you already know something or you feel like you know it and you're relearning it, you're kind of just tuned out because your brain's like, oh, this isn't new information. But if there's too much information, too much new information, like in class, you end up tuning it all out as well because now it just becomes gibberish. And I think, tie this all back to the bar, if the bar isn't high enough, then I actually put in less effort for some reason. So I think there is something about having too much to do that gives me a higher probability of achieving the objective, at least in terms of learning goals. So I think it needs to be balanced because now I've ratcheted it back a little bit, but now I'm like less interested in learning. But maybe that it's always tough to know, right? Because all of these metrics and all of these things that I look at or the changes I make to the system are always a function of how it's going. So hard to tell why it's going the way it is. That being said, we're going to jump in, not do too much talking today and jump straight into the problems. We might skip NIM game. Actually, we might try NIM game again. I didn't read the ADM, so it might just be kind of pointless. But we're going to try NIM game again and then keep going. But don't forget that the HCC needs you. So you're going to want to join the hyperbolic coding chamber. It is a chamber that is growing really really quickly. And so we're going to have to upgrade soon from a chamber to a plaza, a hyperbolic coding plaza. So you're going to want to join for the plaza, the chamber to plaza upgrading ceremony / celebration. So I will see you there, and I'm going to jump into NIM game. And then I'll start the timer. And we have to do the contest, I think tomorrow is when it starts, or Sunday. So you're playing the following NIM game with your friend. Initially, there is a heap of stones on the table. You and your friend will alternate taking turns, and you go first. On each turn, the person whose turn it is will remove 1 to 3 stones from the heap. The one who removes the last stone is the winner. Given n, the number of stones in the heap, return true if you can win the game, assuming both you and your friend play optimally. Otherwise, return false. So n is equal to 4 here. But n is equal to 4. Our output is false, so I can't win the game if we both play optimally. Because there are 3 possible outcomes. I remove 1 stone, my friend takes 3, they win. I remove 2 stones, my friend takes 2, and I lose. Or they win. I remove 3 stones, and my friend removes the last stone, and they win. In all outcomes, your friend wins. In all these outcomes, I win, because I can take 1 stone to win, or 2 stones to win. So I'm wondering if there is... The way we decided to go about this was with a tree-like problem where the top of the tree would be 0 and we're searching for the different paths to 5, and then the level by which we reach 5 will determine who's to the last person's turn it was. This solution had flaky results because I don't think the path that I ended up with was representative of both players playing optimally. So the question is, can a tree represent both players playing optimally? I think it can, because the tree could represent all possible games that could be played just because the game is so simple. But even if we were to generate all those paths, how would we know which one is actually optimal? How would we know which path is actually optimal? How do we know that both players are playing optimally? That is the real question. And maybe that's why this doesn't translate well to a tree problem. Because even if you take the shortest path, there could be multiple paths of that same length. Could be multiple paths of that same length. Then how would we know that I can win? I think this might just be more of a math issue. If the game, or maybe can we boil it down can we boil this whole problem down to a simple approach? If n equals 4, the reason I can win is because we reach 3, and anyone can win if they can reach 3. Now what if we do 6? There's a lot of possible paths if we played 6. I'm going to put in 6. Actually, they have 5 already, and their output is true. So you'd start at 5. I go first. I thought there might be something here with even and odd, but now I'm not thinking so. Oh no, the related topics are math, brain teaser, and game theory. Let's see what the hint is. There are 5 stones in the heap. Could you figure out a way to remove the stones such that you will always be the winner? Maybe the optimally part is red hair. Maybe the optimally part is the red herring. What if I can win at all? What if we just return that? I think that's what we tried before. Such that I will always be the winner. So I don't think this is what they want, because I'm doing if I can win it all, I'll return. But they're saying if there are 5 stones in the heap, could you figure out a way to remove the stones such that you will always be the winner? I remember reading a little bit about game theory, and there's like a couple different strategies. I remember reading it on an AI page. It was like there are like zero-sum games. Then there are ways you can play such that you make the locally the best move, but it's not globally the best move. Like a couple different ways. This is to remove the stone such that you will always be the winner. What if we did this? We don't return anything. And what we'll do is we'll say my wins will be equal to 0. Friend wins will be equal to 0. And then we'll say, okay, if we reach the end, we'll say if turn, then my wins plus equal 1, else friend wins plus equal 1. And then at the end, I'll console.log my wins with friend wins. And we'll just return false for now. I just want to see what that looks like. I just made it constant. My environment is frozen. Let's try that again. They expected false, true, and true. And I think if we say, so my wins were 18, theirs was 20, 3 and 3. So if they're even, we'll take it as my win. If I'm greater, we'll take it as my win. And I think that would actually give us, at least for the test cases, so say if my wins is greater than or equal to friend wins, we return true, otherwise we return false. And I'm going to add 5 as a test case. So it does work including 5, so let's try it. Oh man, I think we figured it out, but it takes too much time. It's unfortunate because we're actually searching from the number itself. So I think like we did a long time ago, starting from, oh wait, no we're not, we're starting at 0. Let me see how large the stack goes up to, or the heap. Oh. Yeah, this would never work. This would never work. It would literally grow to be so large. And then it's like just like coin chains, we end up saying, okay, then we're going to memoize it. While q.length does not equal 0. Is it all paths? We have potentially 2 to the 31 nodes cubed. It's crazy. That's a crazy number of nodes in memory. I don't think there's a way to memoize this because I guess depending on the path, it's who wins. I want to be able to save the values based on the nodes themselves. For example, if we start at 5, who wins if we enter 4 on my turn? My friend does. But I could also win. Actually, no, I always lose there because I can only take it max 1 stone and they always win. Here's a lot of downvotes on this one. I'm definitely thinking this definitely not an easy. N equals 4. n equals 4. N equals 4. I just keep thinking there's a math way to do this one. What if we just divide by 2? If we divide by 2, I can't see this not being represented as a tree. I don't understand how you would encode the optimality of choice just with regular, like, math expressions. You know what? Maybe there is something to this, where it's not. We're not. The math solution isn't about encoding the optimality of choice. Maybe it is just about encoding the actual solution space. So, for example, anything under 3. Let's just do this: 4, 5, 6, 7, 8, 9, and 10. And then we'll see who wins. And then maybe we can encode, there's a pattern in there. And this is a little hard to read, so I'm just going to print. Me friend. I think we're onto something, because it's if whoever wins more seems to be getting the correct answer. I'm also going to, instead of printing the actual wins, actually let me look at the win numbers. It's actually really close. I'm going to print n instead. Four, 5, 6, 7. Okay, this will be the final test. I think 12 gives us TLE. Maybe that's just in. Okay, so they actually does like there's a pattern here. Starting from 4, right? My friend wins 5, 6, 7. Then I win. Then my friend 8, and then I win 9, 10, 11. My friend wins 12, and presumably, if I were to put 13, 14, and 15. 13, 14, 15, and then I should win those next 3 games. Okay, I think there's definitely a pattern here. So what we can just do Okay, we are not close. Oh. I think I had to swap this. Not equals 0. No way. Oh my god. Oh my god. Okay, we may actually be ascending. There is no way I would have figured this problem out 100 days ago. That is actually crazy. No way. That's got to be a constant time, or however many times it takes to do this operation. That is crazy. That is actually crazy. That's so crazy. The other thing I realized is that you don't get TLE when you run the test cases. So I guess you can do some data analysis, and then the part we were talking about, the tree is too large to actually search up to 2 to the 31, and so we just use the BFS as a way to find the pattern, and there's no way that math could encode the optimality of choice, so we just use math to encode the choice. I guess you could. It's not encoding the choice, it's just encoding the pattern. That's just crazy. That is crazy. You can always win a NIM game if the number of stones n in the pile is not divisible by 4. Let us think of the small cases. It is clear that if there are only 1, 2, or 3 stones in the pile, it is your turn. You can win the game by taking all of them. Like the problem description says, if there are exactly 4 stones in the pile, you will lose. So no matter how many you take, you leave some. They can win the game. So in order to win, you have to ensure that you never reach the situation where there are exactly 4 stones in the pile on your turn. Similarly, if there are 5, 6, or 7 stones, you can win by taking just enough 4 stones for your opponent so that they lose. One can pick 3, 2, or 1 stone to ensure that again 4 stones will be left to you on your turn. It's obvious that the pattern repeats itself for n, 4, 8, 12, 16, 4. Wow, that was incredible. This I think there was another problem we solved earlier in maybe 30 days ago, and I said this is why we do the problems for those moments. This is another one of those problems. I definitely know 100 days ago I would have never been able to solve this problem. So that is really cool. Feel strong, man. Can't celebrate for too long. Let's go on to the next one. It's called the flip game. You're playing a flip game with your friend. You are given a string current state that contains only plus. You're playing a flip game with your friend. You're given a string current state that contains only plus and minus. You and your friend take turns to flip 2 consecutive plus plus into minus minus. The game ends when a person can no longer make a move, and therefore the other person will be the winner. Return all possible states of the string current state after one valid move. You may return the answer in any order. If there is no valid move, return an empty list. So we're given current state, contains only plus or minus. Our friend takes turns to flip two consecutive plus plus into minus minus. Okay. The game ends when a person can no longer move. Therefore, the other person will be the winner. Return all possible states of the string current state after one valid move. You may return the answer in any order. If there is no valid move, return an empty list. So it looks like the turn, let me see, there's another example. Current state dot length goes up to 500, and current states of I is either plus or minus. A lot of dislikes on this problem. It looks like on a lot of the easy problems people hate. Game with your friend. Flip two consecutive plus plus into minus minus. Let me just check the mic properties real quick. Okay, we're good. I think this problem also looks like a red herring. I think we just want to know, given a string, can we flip given a string, how many pluses can we flip? So we can flip the first two. We can go to the next index and flip these two. And then we can go to the next index and flip those two. What if we had a string like then you can flip these two, you can flip these two. Well, let's just put it in. We could flip these two, these two, these two, these two. Couldn't flip these two because it's plus minus, then you could flip these two at the end. So let's add some test cases. Plus should return false. Plus 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 should give us two possible flips, unless we have to do consecutive, so we can't leave one in the middle. Expected. Right, so there's only two versions there. I feel like you could just linearly iterate through the string and then flip them if there are two pluses. Return all possible states of the string current state after one valid move. You may return the answer in any order. If there is no valid move, return an empty list. So if current state equals plus plus, minus minus plus 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 minus minus plus plus minus minus plus plus minus 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 plus. I'm just saying anything. Return all possible states of the string current state after one valid move. Return the answer in any order if there is no valid move. I can't tell if I'm underthinking the problem, but a good thing to get into the habit of doing that I'm trying to do is generate counter cases before I write it. If we just check if we can consecutively flip the pluses, I feel like that seems to work, and I can't think of one where it doesn't. If we skip the last index. So maybe we'll try that. State equals current state dot split like this, and then what we'll say is 0 up to state dot length on each do idx end. We want to skip. We want to stay one element before the last one. Right, so if our string is of length 3, right, we're going to go from 0 up to index 2 because we're going to be checking one index forward. They want us to return all different versions of that string. Say strings equal to an empty array. And this should still be okay even if we have one character in the string, because -1 would mean that we wouldn't run at all. And we would say if state sub idx equals plus and state sub idx equals plus, then we shall return. We won't return anything. We'll say strings.push temporary version of the string. The time complexity on this will actually be pretty poor. We'll just say state.join. So we'll join the string back together, and then we'll say string sub idx equals minus. So we'll change those two indices to minuses. So to flip two consecutive plus into minus, right? So that's what we'll do. Then we'll do strings.push stir, and we could do end. So given a string like plus plus plus, we start at 0. Check the first index and the next index, they both equal plus. So we join them. We join the array back together. And we should have used state R so we know what we were talking about. But we join them back together and we change them, those indices, to minus and minus. And then we push the string. We don't want to return an empty array. We want to return stirs. Oh, we didn't do +1. I think that gave us a weird answer. Okay, yeah. I guess that was simpler than we thought. I think the time complexity here actually might be pretty bad. Do state.join, which presumably would take n time. And given a string, we could probably flip every indice. If the whole string was pluses and only the last part, the whole string was pluses, then we could just almost flip the whole thing. Actually, we could flip the whole thing. So it looks like n squared. In terms of each operation or potential moment for operation, it would be idx should be n. Because I think state.join runs in linear time, we do that n times, which would be n squared. But I can't see a way that you would do this without joining it. But I think copying the string in general, maybe there's no way to avoid it because you have to copy the string, which presumably would take linear time. I want to say n squared and n space as well, but I feel like you could make a case for linear time. But we shall move on. Bits. I'm pretty sure I've done this problem before. Apparently I haven't. Given an integer n, return an array ands of length n plus 1, such that for each I is greater than or equal to 0, and I is less than or equal to n. And sub I is the number of ones in the binary representation of I. So we're given an integer array n, 0, 1, 1. Given an integer n, return an array ands of length n plus 1, such that for each I is either is greater than or equal to 0 but less than n, and sub I is the number of ones in the binary representation of I. And I is the number of ones in the binary representation of I. It doesn't quite make any sense, actually. I guess I don't understand the problem. N is equal to 2, we're returning an array of 0, 1, 1. But 0 maps to 0 and 1 maps to 1, then 2 maps to 10. Where is 10 coming from? The binary representation of 2 is like 1, 0. Oh. Oh, I see what they're saying. They want us to actually produce the numbers. So we'd have 0. We're counting up from 0, including 5. 1. The number of ones in 1 is 1. The number of ones... Wait, the number of ones in 2? Or 2's binary representation is 1, 0. They want to know the number of ones in that. Binary representation of 3 is 1, 1. 4 is 1, 0, 0, and 5 is 1, 0, 1. So it looks like the actual problem is given n, count or start at 0, count up, or generate all binary versions of 0 to n. And I think they could have written it like this, I think is what they're trying to say. Generate the number of ones, binary representations of the range I see. So it's generating the number of ones for the binary representation of the range 0, starting from 0 and going up to and including n. Isn't the number of ones in a... Isn't the number of ones in a... I thought the number of ones in a number was called the Hamming weight. So maybe that's what we'll do. We'll call it ham. We'll give it a number. And ham is going to be equal to 0. And what we're going to do is do 32 operations, because I think we're being given a 32-bit number, or not. Want to count the number of ones. If we only count the number of ones, okay, we don't have I don't know if it's 32-bit or 64-bit, so we could do it with division, I think. If we consider, oh, my screen might be really small. Oh, it's not too small. If we consider, for example, the number 5, how would you translate 5 to binary? If we do 5 divided by 2, you get a remainder of 1 with 2 left, and then you do 5 divided by 2 again, you get a remainder of 0. So I think we could do it this way if we do power. So we'll just say that the power, we'll just assume it's a 64-bit integer. But I think we could do the same thing either way. I think let's just try it this way. We'll assume it's a 64-bit integer. And we actually want to go in reverse, which means, yeah, we'll go from 0 to 64, we'll call it rev power. Then we'll say power is actually going to be equal to 64 minus rev power. That way when we start at 60, we'll start at 64 and do minus 0, and 63, and so on. And then we'll put n into a temporary value, and then we'll say if 2 to the power is less than or equal to temp, then we'll say temp minus equal to the power, and then we'll do ham plus equal 1. Now I'm also remembering there's a faster way to do this with and and %1. But we'll try that afterwards. Then we'll say return an empty array for now, except we'll want to put the ham of three, 4, and 5. So So you get 1, 1. No, we don't. Oh wait, I think we do actually. We get 1. We start at 2, and that's the third index. 0, 1, 2, or 2, which is 0, 1, 2. So 1, 2, 1, 2. So I think this works. And then I think all we would have to do is say r equals this, and we'll say starting from 0 going up to including n, we'll say num, we'll say r dot push ham of num. Very slow, actually. Very slow. Maybe we could just go to 32 instead. Oh, and I have to change. It's about the same. I think there's a faster way. I think there's a faster way to get the Hamming weight. I think you can just do while n. We'll just change it. We'll keep a temporary value of n just because it's good not to mutate it, even though it's by value anyway. Or maybe we can just do it like this. It actually might make it simple. We'll say n does not equal 0. N does not equal 0. And we'll say ham plus equal 1. And we'll say n is equal to n and n minus 1. Right, that's much faster. I actually don't remember exactly how this one works, but I know it's just a trick for Hamming weight. It's very easy to come up with a learn time of n log n. Can you do it in linear time and possibly in a single pass? What does that mean? Can you do it in linear time? Oh, I think I see what they're saying. We're treating each number individually. Maybe it just grows over time. So what if we had the number 14? In fact, we'll do it like this. 12, 13, 12, 11, 10, 9. I see what they're saying. You could definitely do this in a single pass because you only technically have to calculate So I think we could actually do this. What if we bring this down to 14? And then we could do this. I think you can do it in one pass because it's all the same number, and because the binary works, you're just turning a bit from 1 to 0. So you don't have to do it for each number. You could just do it for the last number. To do that, though, you need a method of counting the zeros that does visit all the numbers. I think this version, the Hamming weight trick, does work. think the Hamming weight trick does work by removing the most recent 1 bit. So I think one way to check is if we just do puts ham and n. I think our other version worked better for this. The version we had up here, we were just going down. Zero going down. Zero to each. Yeah, we can definitely do this in one pass. I'm just having a bit of a brain. Having some trouble focusing. Temp is equal to n. This version of the Hamming weight already. How are we counting? If we're going from 2 to the power, basically at 0. We're doing a loop from 0 to 64. It's because we need to go in reverse, but Ruby loops can only go from 0 to n. So we're just going to subtract it by the upper bound so that we get the number in reverse. So we're actually starting at 64 in the end. So we're going to do minus 0 to start. So 64 to 63 all the way down to 0. So now that we're at 64, we do 2 to the power and see if we can, is it's actually less than or equal to temp. If it is, then we add 1 to it because it's the Hamming weight. Yeah, my brain is struggling to focus. Brain is struggling to focus. Jump goes to N. Man, I think it's very clear that we can solve this, but I think I'm just having trouble centering. So I think that's a wrap. It's like 1 hour and 6 minutes. So we'll come back tomorrow and wrap this problem up with this single pass version.